Until now, we've been working inside AWS's default network. Today, that changes. We're going to build our own production-style network from scratch using Terraform. This is exactly where every real AWS infrastructure begins. Before you launch applications, before you deploy databases, before Kubernetes, you need a solid networking foundation. By the end of this episode, you'll understand how all these networking components fit together, and we'll build them step by step using Terraform. Imagine you're going to build a new neighborhood. Before you build houses, you first need the land. Then you build the streets. Then you decide which areas are public, which are private, where people can enter, and how traffic moves. AWS works exactly the same way. Before we launch virtual machines, before databases, before Kubernetes, we first need the network where all those resources will live. You might be wondering, AWS already gives us a default VPC. Why don't companies simply use it? The answer is simple. The default VPC is great for learning. It's already configured. Everything works immediately. But in production, companies need much more control. They decide which resources are public, which resources stay private, how traffic flows, which ports are open, which subnets applications should use. Security starts with networking. That's why almost every production environment uses a custom VPC. So, what does that network look like? Imagine a user opens your application. The request comes from the internet. It reaches AWS. Then it enters our virtual private cloud, or VPC. Inside that VPC, we'll organize our infrastructure into different subnets. Some resources will be public, others will remain private. Finally, our application will run inside that network. Don't worry if some of these names are new. During this episode, we'll build every one of these components together. Here's everything we'll build today. We'll start by creating our VPC. Then, our public and private subnets will connect the VPC to the internet. Configure routing, create a NAT Gateway, configure security groups, and by the end of this episode, we'll have a complete networking foundation ready for the rest of our Terraform series. Everything we're building today isn't just an example. This network will become the foundation of the Students Portal infrastructure. In the next episodes, we'll deploy EC2 instances, then databases, later Amazon EKS, and all of those resources will live inside the network we create today. So this isn't throwaway code. We're building the real foundation for everything that comes next. As always, before writing any Terraform code, let's start with the official Terraform documentation. One of the most important habits you can develop as a DevOps engineer is knowing where to find reliable information. Instead of searching random blog posts or immediately asking AI, we'll begin with the Terraform registry. This is the official source maintained by HashiCorp, and it's where you'll find every resource, every argument, examples, and the latest updates. Take a look at the documentation. Every Terraform resource follows a very similar structure. At the top, you'll usually find a short description explaining what the resource does. Then you'll see an example usage section that provides a working configuration. Below that, you'll find the argument reference, which explains every available parameter. Finally, you'll find the attribute reference, listing the values Terraform exports after the resource is created. Once you learn how to navigate this structure, you'll be able to work with almost any Terraform resource. Let's start with the example usage. I like beginning with the official example because it gives us a known working configuration. We'll copy it exactly as it appears. Then we'll adapt it to our own project instead of writing everything from memory. Every piece of infrastructure in Terraform starts with a resource block. This tells Terraform which AWS service we're creating, in this case a virtual private cloud. This is the local name Terraform uses inside our project. It doesn't exist in AWS. It's simply how we'll reference this VPC from other resources. This defines the IP address range available inside the VPC. We'll spend a few minutes talking about CIDR notation shortly. For now, just remember that every VPC needs its own private network. Now that we know how Terraform creates a VPC, let's understand what a VPC actually is from AWS's perspective. Terraform is simply the tool we're using to provision infrastructure. AWS is the platform providing the service. Understanding both perspectives will help you build better infrastructure. Don't worry about every component yet. Throughout this episode, we'll build each one step by step. By the end, this entire diagram will exist in our AWS account, created entirely with Terraform. At the very top, we have the internet. Traffic enters our AWS environment through the NAT Gateway. Inside the VPC, we have multiple availability zones, which are separate AWS data centers within the same region. Inside each availability zone, we create one or more subnets. Those subnets are where we'll eventually deploy our resources, like EC2 instances, databases, and later in the course, even our Amazon EKS cluster. Don't worry if some of these components are still unfamiliar. The goal today isn't to understand every box in this diagram. It's to understand how they all fit together. Before creating our first networking resource, let's make one improvement to our project. Up until now, our Terraform configuration has been relatively small. Keeping everything in just a few files worked perfectly, but starting today, we're going to build much larger infrastructure. We'll have a VPC, subnets, route tables, gateways, security groups, and many more resources in the next episodes. If we keep putting everything into a single file, the project will quickly become difficult to navigate. Notice that we're not creating Terraform modules yet. Modules deserve their own episode. Today, we're simply organizing our code by responsibility. Terraform automatically loads every .tf file in this directory. So, although the code is now split across multiple files, Terraform still treats it as a single configuration. This is a common practice in real Terraform projects because it keeps the code easier to read and maintain. Notice that nothing changed. We only reorganized the project. Terraform still sees exactly the same infrastructure. That's because splitting resources into multiple .tf files changes the organization of the code, not the behavior of the configuration. Now it's time to adapt this example to our own project. We'll keep what we need, modify what doesn't fit our requirements, and gradually build the production-style AWS network we've been designing throughout this series. Let's start with the VPC resource. The example from the documentation is intentionally very simple. It's designed to help us understand the resource, not to fit every project. Our goal now is to take this working example and adapt it to the infrastructure we've been building throughout this Terraform series. We'll make one change at a time so it's clear why we're doing it. Before we create our own VPC, let's look at something Terraform is already showing us. In the outputs, we can see the ID of the default VPC that already exists in this AWS account, and we can see its CIDR block. This is the network range AWS assigned to the default VPC. Let's go to the AWS Console and take a look at it. Here we can see the same VPC ID and the same CIDR block, 172.3.1.0.0/16. So Terraform isn't inventing this information. It's reading an existing AWS resource through the data source we created earlier in the course. Now, what exactly does 172.3.1.0.0/16 mean? This is called a CIDR block. It defines the range of private IP addresses available inside this VPC. You can think of the VPC as our neighborhood, and the CIDR block defines how much address space we have available to build inside that neighborhood. Later, we'll divide this large network into smaller networks called subnets. The /16 represents the size of the network. For this beginner course, you don't need to calculate CIDR ranges manually yet. The important thing to understand is that the VPC gets a large address range, and we'll divide that range into smaller subnet ranges. You might be wondering, well, how did Terraform know which VPC to show in the outputs? Remember, we didn't create this VPC. AWS created it automatically when the account was created. Terraform simply read the existing resource using a data source. If you remember from our data sources episode, this block doesn't create anything. Instead, it asks AWS, give me the default VPC for this account. Terraform retrieves that information and makes it available to the rest of our configuration. This line tells Terraform that we're looking specifically for the default VPC. AWS returns the matching resource, and then we can reference its attributes anywhere in our project. That's exactly how these outputs were generated. Terraform read the existing VPC, retrieved its ID, retrieved its CIDR block, and exposed them through our outputs. So we're not hard coding any of this information. We're reading it directly from AWS. That was useful while we were working with the default VPC. Instead of reading an existing VPC, Terraform will provision one for us. Let's go back to the official example and adapt it to our project. AWS chose 172.3.1.0.0/16 for its default VPC, and we'll use the same one in this course. Following the official examples whenever possible makes it easier to compare our code with the documentation while you're learning. Later, we'll divide this network into public and private subnets as we continue building our infrastructure. We could leave this exactly as it is. It would work perfectly. But remember what we learned in the variables episode. Hard-coded values make configurations harder to reuse, so let's make this configurable. Functionally, nothing changed. Terraform will still create exactly the same VPC, but now our configuration is more flexible. If we ever need a different network for another environment, we only need to change the variable instead of editing the resource itself. Great. We now have our first networking resource. Before creating anything in AWS, let's follow the same workflow we've used throughout the entire course. First, we'll format the code, then validate the configuration, review Terraform's execution plan, and only after understanding exactly what Terraform is going to do, we'll apply the changes. Notice that our outputs are still showing the default VPC. That's because they're still referencing the data source we used earlier in the course. Now that we're creating our own VPC, we should update those references to point to the resource we're managing ourselves. This is a good example of how Terraform configurations evolve as the infrastructure evolves. Perfect. Now our outputs are pointing to the new Students Portal VPC instead of the default VPC. Notice that Terraform already knows the CIDR block because we defined it in our configuration. But the VPC ID says known after apply. That's because this VPC doesn't exist in AWS yet. Since we destroyed the infrastructure at the end of the previous episode, Terraform is now planning to recreate all the resources defined in our current configuration. That's expected. We're starting from a clean environment, so before we continue building the network, we'll apply the existing configuration and restore our baseline infrastructure. Once that's ready, we'll continue adding the networking resources step by step. Great. Terraform finished creating the infrastructure, and now we can verify the VPC directly in AWS. Here we can see the new VPC ID. The VPC is available, and most importantly, we can see the CIDR block we configured in Terraform, 10.0.0.0/16. We can also confirm that this is not the default VPC. So at this point, we've successfully created our own custom network instead of relying on the one AWS provides automatically. This is the foundation that we'll use for the rest of the infrastructure in this series. The VPC now exists, but it's still isolated. If we want resources inside this network to reach the internet, we need to connect the VPC to an internet gateway. So let's go back to the official Terraform documentation and create our next networking resource. We found the official AWS_internet_gateway resource in the Terraform registry. I scrolled through the documentation, reviewed the available arguments, and copied the first working example. This gives us a reliable starting point. Now, just like we did with the VPC, We're going to adapt this example to the student's portal network instead of writing everything from memory. Great! We now have the official Terraform example. Before adapting it to our project, let's take a moment to understand what an Internet Gateway actually is in AWS. So what exactly is an Internet Gateway? An Internet Gateway is the component that connects a VPC to the public internet. Think of it as the front door of your network. Without an Internet Gateway, resources inside your VPC have no path to send or receive internet traffic. It doesn't assign public IP addresses, it doesn't filter traffic, it simply provides the connection between your VPC and the internet. However, attaching an Internet Gateway alone is not enough. Later in this episode, we'll also configure route tables so AWS knows which traffic should be sent through this gateway. Let's verify that in our AWS account. Here we can see the Internet Gateways currently available. Notice that our new VPC doesn't have one attached yet. That's exactly what we're about to create with Terraform. Now that we understand what an Internet Gateway is and why we need it, let's go back to the official Terraform example and adapt it to our student's portal project. Just like we did with the VPC, we're not going to write this resource from scratch. We'll start from the official example and adapt it to our own project. The documentation uses the local name GW. That's perfectly valid, but I prefer using more descriptive names. Since this Internet Gateway belongs to the student's portal project, we'll rename it accordingly. This is probably the most important line in this resource. An Internet Gateway must be attached to a VPC. Instead of hard-coding a VPC ID, we're referencing the VPC we created a few minutes ago. Terraform automatically understands this relationship. It knows the VPC must be created before the Internet Gateway can be attached. This is another example of an implicit dependency, something we learned earlier in the series. Notice how Terraform exposes attributes from one resource that we can reuse in another. This is one of the biggest advantages of infrastructure as code. Instead of creating a completely new tags block, we'll continue using the common tags we've been using throughout the project. This keeps all our AWS resources consistent and follows the same tagging strategy across the entire infrastructure. Terraform is planning to create a single new resource, our Internet Gateway. This line is the most important part of the plan. Terraform is attaching the Internet Gateway to the VPC we created earlier. Notice that we never typed the VPC ID manually. Terraform resolved that reference automatically. At this point, does everything look correct? If the answer is yes, then we're ready to create the resource. Creating an Internet Gateway usually takes just a few seconds. Once Terraform finishes, we'll verify the result directly in the AWS Console. And here it is. Our Internet Gateway has been created successfully. If we open it, we can also see that it's attached to our student's portal VPC. So now our VPC has a connection point to the internet, but we're not done yet. Even though the VPC now has an Internet Gateway attached, resources inside the VPC still can't access the internet. We haven't told AWS how traffic should reach this gateway. For that, we need another networking component, route tables. That's exactly what we'll build next. Great, we now have our own VPC, and we've connected it to the internet using an Internet Gateway, but we're still missing one very important component. At the moment, AWS has no idea where network traffic should go. That's the job of a route table. Let's understand what it is before writing any Terraform code. As always, let's start with the official Terraform documentation. We'll review the example provided by HashiCorp, understand the resource, and then adapt it to our project. So what exactly is a route table? You can think of a route table as a map. Every packet leaving a subnet follows the routes defined in this table. The route table decides where the traffic should go. Should it stay inside the VPC? Should it go to another subnet? Or should it leave the VPC and reach the internet through the Internet Gateway? That's exactly what this component controls. AWS automatically created a main route table when we created the VPC. Every VPC always has one, But for production environments, it's common to create our own route tables and explicitly associate them with our subnets. That's exactly what we'll do throughout this project. Just like before, we're starting with the official example, then we'll adapt it to fit our students' portal infrastructure. At first, this configuration might look a little overwhelming. It contains multiple routes, IPv4, IPv6, and resources that we haven't created yet. The important thing to remember is that the official documentation is designed to cover many different scenarios. Our job isn't to use the example exactly as it is. Our job is to understand it first and then adapt it to the needs of our own project. So let's go through this example one section at a time and simplify it for the students' portal network. We'll start by renaming the resource. The documentation uses the name example, but we want our configuration to be descriptive. Since this route table will be used by our public subnet, let's rename it to public. Next, the route table needs to know which VPC it belongs to. The documentation references AWS _VPC.example, but our VPC is called students _portal. So we'll update the reference. Now let's look at the first route. The destination in the example is 10.0.1.0/24. That doesn't represent what we're trying to accomplish. Our goal is to allow internet-bound traffic. So instead of a specific network, we'll use 0.0.0.0/0. This means any IPv4 destination, and instead of attaching it to the example internet gateway, we'll reference the internet gateway we created in the previous step. The second route is for IPv6 traffic. In this course, we're focusing on IPv4 networking to keep the concept simple. We also haven't created an egress-only internet gateway. Since we don't need IPv6 for this project, we'll remove this entire block. Finally, we'll replace the default tags from the example with the common tagging strategy we've been using throughout the series. Notice what we've done. We didn't write this resource from memory. We started with the official example, understood each section, removed what we didn't need, and adapted the rest to fit our own infrastructure. That's a workflow you can apply to almost any Terraform resource you'll encounter in the future. Now let's format the code, validate the configuration, and see what Terraform is planning to create. Let's review the execution plan one more time. Before running Terraform apply, I always like to confirm that Terraform is going to create exactly what I expect. Perfect. Terraform is planning to create a single new resource, our public route table. That's exactly what we expected. This is the most important part of the route table. We can clearly see the route we configured. The destination is 0.0.0.0/0, which represents any IPv4 destination outside our VPC. And Terraform has already resolved the internet gateway reference for us. Instead of showing the Terraform resource name, the plan now shows the real internet gateway ID that already exists in AWS. This confirms that the route table will send internet-bound traffic through the internet gateway we created in the previous step. We can also verify that this route table will be created inside our students portal VPC. Finally, we can see all the tags that will be assigned to the resource. Since we're reusing our common tags, every resource we create follows the same tagging strategy across the project. Everything looks exactly as expected. Terraform is creating one new resource. It's attaching it to the correct VPC. It's using the correct internet gateway, and all of our tags look correct. That means we're ready to apply the changes. Here we can see the route that Terraform created. AWS automatically includes the local route, which allows communication within the VPC. And right below it, we can see the route we added. Any traffic destined for 0.0.0.0/0 will now be forwarded to our internet gateway. At this point, our network knows how to reach the internet. However, there's still one important piece missing. We don't have any subnets yet. In the next step, we'll create our public and private subnets and then associate them with the appropriate route tables. As always, we'll start with the official Terraform documentation. We'll copy the example first and then adapt it to our own project. A subnet is simply a smaller network inside a VPC. Instead of placing every resource into one large network, we divide it into smaller sections. This gives us better organization, security, and control. Some subnets will be public, others will remain private, and later in the course, we'll decide which AWS resources belong in each one. If we look at our Students Portal VPC, notice that it doesn't contain any subnets yet. That's because Terraform hasn't created them. Let's build our first one. Just like before, we'll start with the official example and simplify it for our own infrastructure. This resource creates a subnet. We'll call it public because resources inside it will eventually have internet access. Every subnet belongs to a VPC. Once again, Terraform creates an implicit dependency because we're referencing our VPC directly. Earlier in this episode, we created our own VPC using the CIDR block 10.0.0.0/16. Think of that as one large private network. A subnet is simply a smaller network carved out of that larger address space. Every subnet must belong to the VPC and use a CIDR range that's contained within the VPC's CIDR block. Since our VPC uses 10.0.0.0/16, we'll create our first subnet using 10.0.1.0/24. Later in this episode, we'll create another subnet using a different range for our private resources. Before we continue, let's make this configurable. Just like we did with the VPC CIDR, we'll create a variable for the public subnet CIDR and reference it from our resource. Let's make one small improvement. I'll move the subnet CIDR into our dev.tf vars file, and while I'm there, I'll also move the VPC CIDR. I realized I hadn't moved that one yet, so now both network ranges are defined in our environment configuration instead of being hard-coded in the Terraform code. Finally, just like we've done with the other resources in this project, I'll replace the simple tags block with our merge function so the subnet follows the same common tagging strategy as the rest of our infrastructure. Now let's validate the changes and review the plan. At this point, Terraform should only be adding our new public subnet. We already know which VPC it belongs to, which CIDR range it will use, and how it will be tagged. Terraform has finished creating the subnet, and now let's verify it directly in AWS. First, we can see the subnet is in the available state, which means it was created successfully. Next, notice the IPv4 CIDR block. It's using 10.0.1.0/24, exactly the value we configured in our Terraform variables. We can also verify that this subnet belongs to our Students Portal VPC, not the default VPC. AWS has also placed it in an availability zone. In my case, it's US East 1F, but this may be different in your AWS account depending on the region and availability zone mapping. One more thing worth noticing is that auto assign public IPv4 address is currently set to no. That's because we haven't configured that behavior yet in Terraform. And finally, notice that the subnet is currently associated with the main route table. In the next step, we'll create our own route table association. So this subnet uses the public route table we created earlier instead of the default one. Right now, our VPC has a route table, and we also have a subnet. But these two resources don't know about each other yet. That's exactly what a route table association does. It tells AWS which route table a subnet should use. Just like we've done throughout this episode, we'll start with the official example and adapt it to our project. This resource creates the association between a subnet and a route table. I'll call it public because we're associating our public subnet. Here we're telling Terraform which subnet we want to associate. In our case, it's the public subnet we created a few minutes ago. And here, we're specifying which route table that subnet should use. We're referencing the public route table we created earlier. Notice once again that we're not hard-coding any IDs. Terraform resolves all these references automatically. That's all we need. This resource doesn't create a new networking component. It simply connects two existing resources together. Let's validate the configuration and see what Terraform is about to change. We can even see the IDs that Terraform resolved automatically for both resources. Everything looks exactly as expected, so we're ready to apply the changes. If we refresh the subnet details, notice that it's no longer using the main route table. Instead, it's now associated with the public route table we created with Terraform. This means the subnet now follows the routes defined in that table. At this point, traffic leaving this subnet knows how to reach the Internet Gateway. However, there's one more requirement before resources inside this subnet can actually access the Internet. They need a public IP address. We'll configure that next as we continue building our public network. Our subnet is called public subnet, but if we look closely, it's not really public yet. Simply naming it public doesn't make it public. There's one more setting we need to configure. This option tells AWS to automatically assign a public IPv4 address to every EC2 instance launched inside this subnet. If it's disabled, instances will only receive a private IP address. That means they won't be reachable from the internet, even though the subnet has a route to the Internet Gateway. By enabling this option, every new EC2 instance launched inside this subnet will automatically receive a public IP address. That's one of the characteristics of a public subnet. Now, the subnet is configured as a true public subnet. Any EC2 instance launched here can automatically receive a public IP and communicate with the internet. Let's pause for a second and see where we are. We have our own VPC, an internet gateway connected to it, a route table with a route to the internet, a public subnet. That subnet is associated with the route table, and now it's configured to automatically assign public IP addresses. At this point, our public networking foundation is complete. If every subnet had internet access, our databases and Kubernetes worker nodes would be exposed to the public internet. That's exactly why we also need private subnets. So far, everything we've built has been focused on the public side of our network. But in real production environments, not every resource should be exposed to the internet. Think about databases. Internal AP is, or Kubernetes worker nodes, those resources should remain private. That's why our next step is to create a private subnet. The good news is that we don't need a different Terraform resource. A private subnet is created using exactly the same AWS_subnet resource. The difference comes from how we configure it, not from using a different resource. I'll duplicate the public subnet and adapt it for our private network. Most of the configuration stays the same. We're still creating a subnet inside the same VPC. We're just changing the network range and the behavior. Here's the key difference. In the public subnet, we enabled automatic public IP assignment. For the private subnet, we won't do that. Resources launched here will only receive private IP addresses. That means they won't be directly reachable from the internet. At this point, we have one public subnet and one private subnet. Let's see what Terraform is going to create. Terraform is planning to create one new resource, our private subnet. We can see it will use the CIDR block. It belongs to our student's portal VPC. Everything looks exactly as expected, so let's apply it perfect. Terraform created the private subnet successfully. Now our VPC has both a public subnet and a private subnet, which is the basic foundation of a production style network. One thing you'll notice is that both subnets were created in the same availability zone. That's because we never told Terraform where to place them. AWS simply selected one for us. For learning purposes, that's perfectly fine. But in production, we usually distribute our infrastructure across multiple availability zones for higher availability and fault tolerance. Let's improve our configuration. Just like we used a data source to retrieve the default VPC earlier in the course, we're now using another data source to retrieve all the availability zones available in this AWS region. Here, we're explicitly telling Terraform to create the public subnet in the first availability zone returned by AWS, and we'll place the private subnet in the second availability zone. Now our network is distributed across two different availability zones, which is much closer to what you'll see in real production environments. We now have both a public and a private subnet, but if you look closely, they're both connected to different route tables. The public subnet is already using the route table we created. The private subnet is still using the VPC's main route table. At this point, that route table doesn't know how to reach the internet, and that's exactly what makes this subnet private. Notice there's no route to the internet gateway here. The only route available is the local route inside the VPC. Resources inside this subnet can communicate with other resources in the VPC, but they can't reach the internet. So, what happens if an EC2 instance inside this private subnet needs to download software updates? Or what if our Kubernetes worker nodes need to pull container images from Amazon ECR? They still need outbound internet access, but we don't want to expose them with public IP addresses. AWS solves that problem with a NAT Gateway. Before we build the NAT Gateway, let's understand why it exists. A NAT Gateway is the bridge that allows resources inside a private subnet to access the internet without exposing them to incoming traffic. But a NAT Gateway can't communicate with the internet by itself. It needs a public IP address. That's where the Elastic IP or EIP comes in. An Elastic IP is a static public IP address provided by AWS. We attach that Elastic IP to the NAT Gateway and then place the NAT Gateway inside our public subnet. Now, when a resource inside the private subnet needs to download updates, install packages, or pull container images from Amazon ECR, the traffic flows through the NAT Gateway, which uses the Elastic IP to communicate with the internet. The important thing is that the instances inside the private subnet never receive a public IP address. They remain private while still having outbound internet access. This is the architecture you'll see in most production AWS environments. At this point, we know why we need a NAT gateway. But before we can create one, there's one dependency we need to satisfy. A NAT gateway requires a public static IP address. In AWS, that's called an Elastic IP, or simply an EIP. So let's start by creating the Elastic IP, and then we'll attach it to our NAT gateway. As we've been doing throughout this course, we'll start with the official Terraform registry. We'll copy the basic example, understand what each argument does, and then adapt it to our own infrastructure. The example from the documentation associates the Elastic IP directly with an EC2 instance. That was a common approach in the past, but it's not what we need for our architecture. Our goal isn't to give an EC2 instance a public IP. Our goal is to give a NAT gateway a public IP so it can provide outbound internet access for our private subnet. So let's adapt this example to match our environment. Instead of attaching the Elastic IP to an EC2 instance, we'll create a standalone Elastic IP that will attach to the NAT gateway in the next step. You'll notice the official example includes an explicit depends _on. Normally, Terraform can automatically detect dependencies when one resource references another. For example, the NAT gateway already depends on the Elastic IP because we're using a ws_eip.nat.id. However, The Terraform documentation recommends adding an explicit dependency on the Internet Gateway. This ensures the Internet Gateway is fully created and attached to the VPC before AWS attempts to create the NAT Gateway. It's a good example of when an explicit dependency is useful, even if there isn't a direct reference in the code. This is exactly the kind of situation we discussed in the dependencies episode. Most of the time, Terraform figures out the order automatically, but occasionally, the official documentation recommends using depends_on to make that dependency explicit. Great. We now have the two components the NAT Gateway needs, an elastic IP and a public subnet. The NAT Gateway will live inside the public subnet and use the elastic IP to communicate with the internet. But our private subnet still doesn't know that it should send outbound traffic through this NAT Gateway. To solve that, we need a separate route table for the private subnet. This looks very similar to our public route table, but there's one important difference. The public route table sends internet-bound traffic to the Internet Gateway. The private route table sends internet-bound traffic to the NAT Gateway. That's what allows resources inside the private subnet to reach the internet without receiving a public IP address. And finally, we associate our private subnet with the private route table. At this point, the traffic flow becomes private subnet to the private route table to the NAT Gateway, through the public subnet, and then out to the internet. Let's review the plan. Terraform should create the elastic IP, the NAT Gateway, the private route table, and the route table association. If everything looks correct, we'll apply the changes and verify the complete traffic path in AWS. You'll notice that creating the NAT Gateway takes longer than the other resources we've created so far. That's completely normal. Unlike a route table or a subnet, a NAT Gateway is a managed AWS networking service, so AWS needs a little more time to provision it. Once it's ready, Terraform automatically continues creating the remaining resources. Let's take a look at our architecture. We now have our VPC, a public subnet, a private subnet, an Internet Gateway, and a NAT Gateway. The public subnet reaches the internet directly through the Internet Gateway. The private subnet reaches the internet through the NAT Gateway without exposing resources to inbound traffic. This is the foundation of most production AWS environments. We've built the network path itself, but there's one final networking component we promised at the beginning of the episode: security groups. Route tables decide where traffic goes. Security groups decide what traffic is allowed. So before we close this chapter, let's create one security group for the Students Portal Network. We already covered security groups back in episode 4, Resources and Dependencies. So instead of explaining the concept again, we'll simply adapt one for our Students Portal infrastructure. Here we're creating a security group inside our VPC. Then we allow inbound HTTP traffic on port 80, HTTPS traffic on port 443, and finally, we allow all outbound traffic. We'll attach this security group to our EC2 instance in the next episode, when we deploy our first application server inside this network. Everything looks good. Terraform is about to create our security group along with its inbound and outbound rules. Once the deployment finishes, our networking foundation will be complete. Let's apply the changes and verify everything in the AWS Console. We can see that Terraform successfully created our security group. It's associated with the Students Portal VPC we built throughout this episode. If we look at the inbound rules, we can see exactly the two rules we defined in Terraform: HTTP on port 80 and HTTPS on port 443, both accessible from anywhere. And under the outbound rules, we can see that all outbound traffic is allowed. At this point, our networking foundation is complete, and this security group is ready to be attached to the EC2 instance we'll launch in the next episode. Let's take one final look at everything we've built today. We started with an empty AWS account and created a complete networking foundation using Terraform. We built our own VPC, public and private subnets, Internet Gateway, NAT Gateway, route tables, Elastic IP, and finally our security group. This is the same foundation you'll find behind many real production environments running on AWS. Before we wrap up, let's do one more thing. Throughout this course, we've been using AI as an assistant, not as a replacement for the official documentation. Now that everything is working, let's ask AI to review our code and suggest possible improvements. This is a great habit to develop. First, make it work. Then, ask AI to help you refactor and improve your code. Let's see what AI recommends after reviewing our project. First, it suggests avoiding storing AWS credentials in our Terraform variables and using AWS profiles or IAM roles instead. It also recommends locking the Terraform and AWS provider versions to make deployments more predictable. Another recommendation is to use a remote backend, such as Amazon S3, for storing the Terraform state in production. It also suggests improving variable validation, keeping a consistent naming convention across resources, and continuing to use common tags throughout the project. Finally, it recommends adding automated checks like Terraform FMT and Terraform Validate to CI/CD pipelines. Most importantly, notice that AI didn't ask us to rewrite the entire project. Instead, it suggested small improvements while preserving the behavior of our infrastructure. The good news is that many of these recommendations are actually topics we'll cover in the upcoming episodes, such as remote state, modules, and Terraform best practices. So it's great to see that AI is reinforcing the same learning path we're following throughout this course. This foundation is now ready to host our applications. To avoid unnecessary AWS charges, we'll destroy the infrastructure for now. Don't worry, because we're using Terraform, we can recreate everything with a single command in the next episode. In our next lesson, we'll bring this infrastructure back, launch our EC2 instance, configure a key pair, use user data to bootstrap the server, and deploy our first application inside the network we built today. Thanks for watching, and I'll see you in the next episode.